We have said that oxidation is the loss of oxygen when you define it in terms of oxygen. It is the gain of hydrogen when you define it in terms of hydrogen. And at the same time, it is the loss. Sorry. It is the addition of electrons, okay? When you don't know those definitions of the two terms, we are under the topic of redox titrations. When you don't know about those two terms of oxidation and the reduction, we get problems. Oxidation, loss of electrons, or you can say removal of electrons, addition of oxygen, that is in terms of oxygen, and in terms of hydrogen is the removal of hydrogen. But for reduction, the story changes. For reduction, it can be defined as addition of electrons of course to a substance, then it can be removal of oxygen from a substance, then we can also say addition of hydrogen a substance. So that is what we call oxidation, and this is what we call reduction. Right, so now we've said that in redox titrations, we shall specifically be looking at these two terms in terms of electrons. In terms of electrons. Then I've told you that we've got the common terms which we use in redox reactions, and the first common term is what we call the oxidation number, whereby we have said that the oxidation number, or we need to say that the oxidation number of an atom is the real charge or hypothetical charge. Okay, real charge that the atom bears in its pure state. Real charge or the hypothetical charge that an atom bears in its pure state or in its compound, based on specific rules. All right. Now, when the oxidation number of a substance increases, okay, the substance is said to be oxidized. When the oxidation number increases, the substance is said to be oxidized. And when the oxidation number decreases, the substance is said to be reduced. Okay, because when oxidation takes place, remember, there is loss of electrons. We are going to see how this is, how true this is. In the due course, we are going to see how true that is. From here, let's also first talk about another point. And the point we are going to talk about is the oxidizing agent. What is an oxidizing agent? Remember, At the end of it all, at the end of the day, we need to know how redox reactions are written, how redox equations, how the equations for the redox reactions are written, okay? So now, what is an oxidizing agent? In your own words, what is an oxidizing agent?
I think it is a catalyst that enables the loss of electrons.
A catalyst? Let's don't call it a catalyst. Let's say an oxidizing agent is that substance that removes electrons from other substances. A substance that removes electrons from other substances. What happens in the process? In the process of removing the electrons from other substances, the oxidizing agent gains. Because you've said that oxidation is the removal of electrons from substances. So a substance that removes electrons from others is what we call an oxidizing agent. And in the process of removing electrons from others, the oxidizing agent gains those electrons. And as a result, the oxidation number decreases. And therefore, an oxidizing agent is always reduced at the end of the redox reaction. It removes electrons from others. Okay? And the process of removing electrons from others, it gains them by itself, and the oxidation number of the other substance decreases. Therefore, we shall find that an oxidizing agent will always be reduced. The term number 3 is what we call a reducing agent. A reducing agent, you need first to know what reduction is. We've said that reduction is the addition of electrons to a substance, meaning that a substance that adds electrons to another, or which donates electrons to another substance, is what we call a reducing agent. And in the process of donating of electrons, it loses them. And when it loses them, what happens? The loss of negative charges, or in form of electrons, results into an increase in the number of positive charges, okay? Which corresponds to an increase in the oxidation number. And therefore, a reducing agent is always oxidized at the end of a redox reaction. So you need to know that an oxidizing agent is always reduced, while a reducing agent is always oxidized. We're going to look at the details when we start looking at the examples of the reactions. Then we've got what we call the half equations. We've got what we call the half equations. Half equations. Half equations. When we say half equations, these are separate equations that specify which substance gains or loses electrons in a redox reaction. So we are going to look at the details, but half equations, there are two separate equations, or there are separate equations that specify which substance loses or gains electrons in a redox reaction. Then we have got what we call the overall equation. When we say the overall equation now is the equation that is obtained after combining the two half equations, whereby one half equation will be representing oxidation and another half equation would be representing reduction. So by combining the two, we shall be getting what we call the overall equation. All right, so now let me take you to writing these equations. How do we write these equations? Before we clearly look at how we write these equations, we need to first know common oxidizing agents and common reducing agents. We need to first know common oxidizing agents, okay? Now, the common oxidizing agents that we normally consider in practicals include the following. Common oxidizing agents include the following. We've got what we call acidified manganate 7 ions or permanganate ions, acidified manganate 7 ions. Acidified, so this one is written as MnO4 H plus, MnO4 minus H plus. So this is acidified manganate 7 ions. 2, we've got what you call acidified dichromate 6 ions. Acidified dichromate 6 ions. And this is Cr2 O7 2 minus H plus. This is acidified dichromate 6. Then we've got what we call acidified chromate 6 ions. Acidified chromate 6 ion. And this is Cr042 2 minus acidified. So that is acidified chromate 6. We've got what we call the acidified chlorate ions. Acidified chlorate ions. Acidified chlorate, first write a chlorate, ClO3 minus, then an acid. Then we've got another oxidizing agent, acidified oxochlorate. Acidified oxo or oxochlorate ions, and this is IO3 oxochlorate. Sorry, I've written for iodate. Sorry, oxochlorate, that is ClO, then H, first this is minus, then H plus. Then we've got what we call the acidified iodate. Acidified iodate ions, and this is IO3 minus H plus. Then we've got what we call acidified hydrogen peroxide. Acidified hydrogen peroxide. So when we say acidified hydrogen peroxide, of course, you first write hydrogen peroxide, then an acid. Then we've got what we call acidified manganese for oxide. Acidified manganese for oxide. And we write acidified manganese for oxide as MnO2 H plus. Then you've got what we call let me say acidified manganate 6 ions. Acidified manganate 6 ions, and those ones are written as MnO4 2 minus H plus. Then we've got what we call let me say we've got what we call the concentrated sulfuric acid. We all know from our O-level chemistry that conc sulfuric acid is a strong oxidizing agent. We've also got what we call the persulfate ion, very common, persulfate ions. Persulfate ions, one can call them peroxidal sulfide, peroxodisulfate ions, okay? Peroxidal sulfate ions. And these are written as S2O8 2-. We've got what we call oxygen. Remember, oxygen is an oxidizing agent. So oxygen is written as O2. We've got what we call concentrated nitric acid. Conc nitric acid is also an oxidizing agent, etc., etc. So, but in common cases, in our labs, practically, we use these oxidizing agents. All right. Now, interestingly, after having gotten this, now we can go ahead to know how we write half equations, okay, of these reagents, these oxidizing agents. How do we write half equations for them? We've got also these substances like the copper 2 ion can undergo oxidation. Iron 2 is also a strong oxidizing agent which can be reduced to iron. Silver ion can be reduced to silver. Chlorine can be reduced to chloride, etc. So let's write how these, let's see how the half equations of these are written. We are going to write for a few because the practice has to hold us for good. Now, half equations of those common oxidizing agents. Half equations for common oxidizing agents. Because if you don't know how to write half equations, then you cannot tell me that you can easily write a general equation or an overall equation. So if we are to begin with manganese, rather the manganate 7 ion or the permanganate ion, okay, we shall have MnO4, writing for the permanganate aqueous. All right. Remember, we said that an oxidizing agent is a substance which removes the electrons from other substances. So we are saying that in the process of removing electrons from others, it gains those electrons. So an oxidizing agent gains those electrons. So that's why you have written plus E. And when it gains those electrons, remember it is acidified. Actually, I would have done it better by bringing the acid first, okay? I'd have done it better by bringing the acid first. Let me repeat it from here. It is acidified manganate 7. So it removes electrons from others and it gains them. Then after gaining them, it will be reduced from manganate 7 to manganese 2. The oxidizing agent is reduced at the end of the redox reaction. And of course, plus water. So this is what we call a half equation, but it is not balanced at all. And here, that is why I want you to put your practice, so that in case you're writing any redox equation, and in case you're writing for anything to do with an equation, you don't waste much time. You can see that here you have 4 oxygens, but here you have 1. Bring a 4 here. It makes hydrogen 8. Bring 8 here. Manganese is 1, manganese is 1. Now you balance the ions. How do I balance the ions? How do I balance the ions? This side you have 8 positives, while this side you have 2 positives. So, but electrons are negatively charged, meaning that to balance these, no. Actually, this side I have 7 because it is 8 plus -1, the charge. So this side I have 7 positive charges, and this side I have 2 positive charges. So to balance them, I have to put 5 electrons, so that these electrons, we take them, they are negatively charged. So the equation is balanced. And this is the half equation for acidified permanganate ions. Is it okay, my friend?
This part of counting the ions.
Balancing the ions.
You considered balancing.
These ones
how many
were 8.
positive
These ones
ions
were
you
8.
consider?
8 positives,
Then this one
isn't
is
it?
1.
This is -1. So 8 plus -1, you get 7 positive charges. But this side you had 2.
Okay.
So to balance them, you have to subtract 5. And to subtract 5, you have to put 5 on electrons. Is it okay?
Yes.
For purposes of an exam, you have to practice, because in an exam, you may not waste too much time on this. You have to practice and know that for potassium, for manganate 7, I have to put an 8 on hydrogen, I have to put a 5 on electrons, and a 4 on water. This one you have to know it. Even some students go ahead to know the overall equation, because we are not interested in the half equations. Maybe in case in theory, they ask you to write them, but we are interested in the overall. Let's write for acidified dichromate. Acidified dichromate 6. So it is Cr2, O7, 2 minus, since it is also acidified, and it gains those electrons, it removes from others. Itself would be reduced to chromium 3 ion and automatically water. Chromium, we have 2. Here, we have nothing, so we put a 2 here. We first balance atoms. Oxygen, we have 7, but here we have 1. Put 7 here. Making hydrogen 14, put 14 here. Everything is balanced. Now balance the charges. Here we have positive 14, minus 2, because these are negative. Then minus, okay, let's first leave electrons. So minus 2. This one brings it to positive 12. But this side you have positive 6. This 2 multiplies here. So we have positive 6 this side. So how do we make this equal to this? How many electrons should I subtract here? 6. Is it okay?
It is okay.
The moment you learn how to write these equations, then we are very safe. Let's write for chlorate ions, acidified chlorate ions. You have ClO3 minus acidified, gaining electrons. We say that since it is a chlorate, it is reduced to a chloride ion and water. How do we balance? Chlorine 1, chlorine 1. O3, O1. Put here 3, making hydrogen 6. Put here 6. After putting there 6, you balance. This side we have only -1. But here we have positive 6 minus 1. This is it. Positive 6 minus 1. So we have 5 this side. Well, this side we have negative 1. So how do you balance it? By putting here negative 6. When you put a negative 6 and positive 6 will cancel. So we have negative and this side negative. Is it okay?
It is okay.
Then let's look at how to write for an oxochlorate. An oxochlorate is Cl or just minus. An acid, add an acid. Add electrons. Still, the moment you see Cl, just know it is going to be reduced to a chloride. It's going to be reduced to a chloride and water still. But the way you balance it will now change. Cl1, Cl1. Oxygen 1, oxygen 1. Hydrogen 2, hydrogen 1. So here you put a 2. After putting here 2, this is positive 2 minus 1. Remain with the positive 1. But we want negative this side. So we shall put 2 electrons to balance it. If you have acidified iodate, iodate ion. When iodate ion is acidified, it will act as an oxidizing agent by gaining the electrons it has. It gains those electrons, which it removes the other side. When the acid is concentrated, when the acid used, now for iodate, you need to note what type of acid have they used. If they have used the concentrated acid, the iodate will be reduced to iodide ion. And we shall form water. That is when they have used the concentrated acid. But if dilute acid is used, the iodate ion will undergo oxidation by gaining electron. Now, the iodate is going to be reduced to iodine solution and water. So it has to be as a result of which acid have they used. I know now you can balance. Allow me balance properly. Nothing here. Oxygen 3, put here 3. Hydrogen 6, put here 6. On hydrogen, there is a 6. Then on electron, there we shall also put a 6. That one you can check. Iodate, here is 2 iodines, so we shall put here 2, making oxygen 6. We put here 3. A 6, sorry. A 6, hydrogen 12. So we shall put here 12 also. Then balancing it, you find yourself putting here 10 electrons. Can I continue, Sebo?
This last one.
The balancing, I want you to put that spirit into yourself. Because I've said that you form the products according to type of the acid used. If they have used the concentrated acid, you'll form iodide. If they have used the dilute acid, you form iodine. Then balancing, as usual. Iodine had 2. You have 2 iodines, but this side you had 1. So I put here 2. Oxygen is 6 of them. Put here 6 to balance oxygen. Hydrogens, they have become 12. Put here 12 on hydrogen. Then now balance electrons. This side you have negative 2 plus 12, which is 10. But this side you have no charge. So you have to put 10 so that you get negative 10 plus 10, which is 0. Is it okay? So you have to always look at what you're given and you take your time to balance. But practice matters. It is the practice that is going to make it specific. Is it okay?
Yes.
Then There are very many, but let's write for more. Let's write for more. If it is hydrogen peroxide, acidified hydrogen peroxide, it will gain electrons to form. Hydrogen peroxide is reduced to water. Just that. Nothing much. Hydrogen 2 plus 1, they become 3. But this side you have 2. So you first make this one an even number, like balancing equation. So we put here 2. Hydrogen become 4. We put here at 2. They also become 4. We don't have any charge this side, but this side you have positive 2. So to eliminate it, to balance the charges, we shall put here 2 electrons. Isn't it? Then we've got manganese 4 oxide, acidified manganese 4 oxide. If you have acidified manganese 4 oxide, gaining electrons to form. If it is manganese 4 oxide, you will go to manganese 2 ions and water. Manganese is 1. Manganese is 1. Oxygen is 2. Oxygen is 1. So can you bring a 2 here? Making hydrogen is 4. Can you bring a 4 here? This side you have positive 4 charges. This side you have positive 2. So what should I put here?
You put 2.
I'll put a 2. Oxygen gas is an oxidizing agent, but it's not we don't have acidified oxygen. So oxygen gas will gain electrons. When oxygen undergoes oxidation, we form a peroxide. It is reduced to a peroxide ion. That is a peroxide. Oxygen is 2. Oxygen is 2. Oxygen is 2. Oxygen is 2. No charge this side, but this side we have negative 2. So here I will put 2 negative so that they are the same. Then we have a persulfate or a peroxodisulfate. S2 or 8 is what we call a peroxodisulfate ion. So it will undergo, it is not acidified also. It will gain electrons to form. This peroxodisulfate or the persulfate, it is reduced to a sulfate ion. It's reduced to a sulfate ion. So balancing, you have S2, S, just put here 2. Oxygen is 8, oxygen is 8. It is okay. 2 minus. This side we have 4 minus. So we have to promote them so that they become -2 plus -2, -4, which is the same as -4. Is it okay?
It is okay.
Then we've got what we call, what have I not written about? Acidified chromate 6 ions. Acidified chromate 6 ions, CrO42 minus plus 8 hydrogen. No, actually, I have it in head balance, but you can now, from the experience we've gotten, of course, we shall add, is it 3 electrons? Yeah, we shall form chromium 3 ions and 4 water molecules. For normal elements like copper 2, it gains 2 electrons and it is reduced to copper solid. Iron 2 gains 2 electrons and is reduced to iron solid. Iodine aqueous gains an electron, actually 2 electrons, and is reduced to iodide ions. This is just a quick check. Silver, however, practically not common, but it gains an electron from silver solid. Chlorine gains 2 electrons from chloride ions. Bromine gains 2 electrons from 2 bromide ions. So these are the commonest oxidizing agents that we are having and how they undergo oxidation or how they are reduced at the end of the redox reaction. Can I go to reducing agents?
Yes.
Reducing agents, I may not first outline all of them, but I'm going to outline them as I write their equations to save time. Reducing agents, common reducing agents. When we say a reducing agent, we have already seen that reducing agents, they get oxidized at the end of the reaction. For example, magnesium metal. Magnesium metal is a solid. So for them, we've already said that reducing agents donate electrons to others, so they lose those electrons. Now, if magnesium metal is to lose electrons, it is going to be oxidized to magnesium 2 ions, and it will have lost those 2 electrons. Even the equation is balanced like that. The same applies like to zinc. Zinc metal loses electrons and is oxidized to zinc ion after having lost 2 electrons. The same applies to iron 2. Iron 2 can also undergoes reduction. It can undergo reduction and is oxidized to iron 3 after having lost 1 electron to balance. Then we've got what now we've gone to the commonest. Even this one is very common. All these ones are common. So let's go to an oxalate. An oxalate ion. Oxalate ion is written as C2O4 2-. One can call it ethane dioate ion. So the ethane dioate ion C2O4 2- undergoes reduction and is oxidized to carbon dioxide gas after having lost some electrons. But how many electrons? Carbons are 2, so balance them 2. Oxygens are 4, these are 4. Electrons are 2, this side we have 1, so let's put here 2. So an oxalate ion is oxidized to carbon dioxide gas. Then we've got what we call a thiosulfate ion. A thiosulfate ion, it is S2O3 2-. A thiosulfate ion, for it undergoes reduction and gets oxidized to a tetrathionate ion, S4O6 2- aqueous, after losing some electrons, but S's are 2, S's are 4. So we put here a 2, making oxygen 6 and oxygen 6 balanced. Atoms are balanced. Ions, this is -4, this is -2. Put here a 2, so that -2 plus -2, they become 4. And that is how we balance it. We've got what we call a sulfite ion, not a sulfate, but a sulfite ion. A sulfite ion undergoes reduction, but this process takes place in presence of water. It takes place in presence of water, and the sulfite ion gets oxidized to a sulfate ion, and we shall also produce hydrogen ions. Of course, the process involves the donation of electrons. Sulfite undergoes reduction in presence of water. The same applies to a nitrite. It also undergoes oxidation in presence of water. So now what happens is balancing this, sulfur 1, oxygen 3 plus 1, 4. These are 4. Hydrogen is 2. This is 1. Put here 2. Atoms are balanced. Electrons or ions, charges. This is +2 plus -1. That is. This is +2 plus -2. That is 0. Then -1, -1. This, sorry. This is -2, so here I will put a 2 because these ones will cancel. +2, -2, these ones have cancelled, but this is -2, -2. So that is how a sulfite undergoes reduction. Then a nitrite undergoes reduction still also in presence of water, liquid, and we shall form, it gets oxidized to a nitrate, rather a nitrate, sorry. It gets oxidized to a nitrate, and hydrogen ions, and I guess 2 electrons. The moment you understand the logic, then you are done. We've got what we call the hydrogen peroxide. Also, we've looked at in the previous, when hydrogen peroxide is acidified, it acts as an oxidizing agent. But when it is just hydrogen peroxide, it acts as a reducing agent. So hydrogen peroxide is oxidized to oxygen and hydrogen ion, of course, electrons. Hydrogens are 2, 1. So we put here 2. There is no charge this side, so we have to make them -2 also. So that -2 plus 2 is 0. Then we've got what we call iodide. The iodide ion is a reducing agent which is oxidized to iodine and 2 electrons. We've got tin 2 ion. Tin 2 ion is a very strong, or is a reducing agent which gets oxidized to tin 4 ion, but because of +2 and +4, we shall add 2 electrons. Okay, so these are the most common oxidizing and reducing agents that I can put across. Now, the basic thing now is to write. We've seen how the half equations are written. Okay, we've seen how much the half equation or the half equations are written, and therefore we shall have how we shall see how to write the overall equation. We shall see how to write the overall equation. So you need to always first know how to write the half equations. After writing the half equations, we can see how to write the overall equation. Well, so we want to see how to write the overall equations. Interestingly, if you look at an example of acidified potassium manganate 7 solution, okay, let's write the equation between acidified potassium manganate 7 solution acidified potassium manganate 7 solution. Let's write the equation between that and can begin with shall consider it with iron, 2 ions. This is oxidizing agent, and this is a reducing agent. So it's a matter of first writing the half equations, then later you combine them. Okay. So since we have another thing, like for theoretical or for theory questions, you need to know that when we say acidified potassium manganate 7 solution, and someone says acidified potassium permanganate solution without put, it can be manganate 7 or permanganate. Okay, we shall see during the titrations. Okay, I'll give you a clue of what you would expect to happen. Potassium permanganate is only acidified with sulfuric acid, not hydrochloric acid, because it's a very strong oxidizing agent that oxidizes the chloride ions, okay, in the acid to chlorine gas, and therefore it would be very, 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 very hard. Even the nitric acid is not used because nitric acid itself is an oxidizing agent that would compete with the acidified potassium permanganate, which is also an oxidizing agent. So most of the reactions or the numbers you do are always redox. If it is bare redox titration, they bring a redox reagent or redox reagents, an oxidizing agent and a reducing agent. For example, for this case, one can write the equations. For potassium permanganate, one will write the half equation as Mn or 4 2 minus. This work, you can do it from behind, you cross and you give us the, and we need the overall equation. So plus, we've said that here we have 8 plus, to reflect back, then we add 5 electrons from manganese 2 and for water. Then for iron 2, we shall have that iron 2 being a reducing agent will be oxidized to iron 3 plus electrons. These are the equations we derived together. So now, if you have to write the overall equation for this reaction, first look at electrons, balance electrons. Electrons here we have 5, but here we have 1. So you have to multiply a 5 here, and you have to multiply a 1 here, so that you balance them. Then your overall equation will be when you have balanced this equation. So it will be manganate this manganate, no, there is no 2, it is just minus. Okay, sorry for that. So it is manganate plus 8 hydrogen ions plus, since the electrons are balanced, they will cancel 5 electrons, 5 electrons. So we shall add 5 iron to ions. This 5 will affect this, so it will be 5 iron to ions to give us 1 manganese, 2 iron plus 4 water molecules and 5 iron, 3 ions. Is that okay?
It ends with 5 and 3 ions. Yes.
Order may not matter. You can begin the product with iron 3 ions, provided all the products are on their side. But when you have considered it, this value of multiplied.
Yes.
Okay.
Yes.
Okay. Let's write one more. A case where we have the oxalate ions and manganate ions. Acidified manganate 7 ions and oxalate ions. It's a matter of knowing how to write the half equation. Is that okay? So
Yes.
for oxalate, we say that we form and this one the manganate, we add 8 hydrogens. You have to learn these things so that you don't always waste time balancing. Plus 5 electrons, we shall form manganese 2 plus 4 molecules of water. Now, here electrons we have 2, while here we have 5. You cannot multiply. So you can put a common multiplier that will make them the same. For example, the LCM is 10. That's what I normally tell students. If the LCM is 10, you have 5 and 2, multiply here 2, multiply here 5, so that they are 10, both. So your equation will be 5 oxalate ions, 5 oxalate ions plus, because these are all reactants, so plus 2 manganate 7 then plus 16 hydrogen ions forming 10 carbon dioxide molecules plus 2 manganese 2 ions plus 8 water molecules. Is that okay?
It is okay.
I'm going to end with this. Because I want at the end of the story, I want you to do some of the questions or whatever question we shall be meeting. We should be able, or you should be able to write these redox titrations, rather the redox reaction equations. Let's write about a manganate and a sulfite. Manganate and a sulfite. Sulfite and acidified manganate ion. You already should be knowing how to write the half equations. For a sulfite, we say that it is SO3 2 minus, and it takes place, the reduction takes place in presence of water to give a sulfate. Then for manganate, that one is common, MnO4 plus 8 hydrogens plus 5 electrons to give manganese 2 plus 4 water. Right. What should we multiply? What should I multiply here? You have 2 electrons, you have 5. What should I multiply?
5 then 2.
Okay. So the overall equation will become 5 sulfite plus 5 water molecules. First write it like that. Plus 2 manganate plus 16 hydrogens, giving 5 sulfate plus 10 hydrogen ions plus 2 manganese ions, manganese 2 ions, then plus 8 water molecules. Now, this equation can be simplified by you bringing the water molecules this side and the hydrogen ions this side. You collect like terms, right? So you'll have 5 sulfite plus 2 manganate. You correct like terms taking to where you have many molecules. Now you could not bring the 16 to this side of 10. You would have minus 10 hydrogen ions, and our chemical equations do not involve negative, that this minus this molecule minus this, no. So we shall say plus 16 minus 10 hydrogens will be 6 hydrogen ions to give us 5 sulfate plus 2 manganese 2 ions, then of course plus, when 5 molecules of water come this side, this water will reduce to 3 water molecules. Is that okay? So this would be our overall equation. Is it okay?
Yes.
So I want you to take your time And you write for me the redox equation between hydrogen peroxide and acidified manganate 7 ion. You write that equation. Another equation which I want you to write, I need to write about a nitrite ion with acidified manganate 7 ion. Then I want you to write an equation of acidified potassium dichromate 6, that is Cr2O7 2 minus, with the iron 2 ions, and then still you write Cr2O2 rather O7 2 minus acidified with oxalate iron practice matters. So from there, now you can be safe to interpret a question when you know that with an equation you can solve the equation you can solve the question to the final answer. So we shall begin from there. I'm going to upload the question. I've already uploaded to the question. So we are going to interpret that practical question. I'll provide results in the table, which are already there. And then we interpret it and we calculate. I wish you a good night.
You too.